Hello, everyone, and welcome to our live session. This is the last live session of 2025. My name is Matthew. I am one of the course staff. I work on a lot of stuff behind the scenes, and I will be the moderator for the live session today. Thank you for joining us. We are excited to be here with you, celebrating the sort of beginning of the holiday season and this winter holiday season. And we're going to have a great live session today. Let me give you a rundown quickly of how this works, and then I will turn it over to Chris, who will get us started with a topic of discussion, and then we'll hit some questions from the participants. So please post your questions in the chat. I moderate all those questions, so keep your questions at a beginner level, where this is an introductory level kind of discussion. So keep those at a beginner level. I try to take questions generally in order that they're asked, but I will jump around so that more people, everybody hopefully who has a question at least has a chance to get one question asked. So ask your most important questions first, in case we don't have time to swing back and get to the rest of those. Post those in the chat. I will grab them from there. And we also try to get a variety of topics. So sometimes we'll, if we have a lot of questions about black holes, we'll pop around to some other questions to give people a chance to have those topics discussed as well. We do see all of your questions in the chat, even if I'm skipping around. It's not because we haven't seen them, so please don't spam the chat with repeated questions. And then we do offer, for those of you who are here from our online classes, we offer online classes. So if you're interested in learning more about astronomy, make sure you check out our Coursera and our Udemy classes. We have 3 Coursera courses on astronomy, astrobiology, and the history and philosophy of science. If you haven't taken all of those, I encourage you to scroll up and click that link and sign up for those courses. I think that's it. Please hit the like button and subscribe to our channel so you can hear about upcoming live sessions. Chris, why don't you welcome everybody and then we'll get started.
Okay, hello everyone for our last live session of the year. And welcome however you arrived here. If you're taking one of the courses, great. If not, consider the courses, but we're welcoming you too. To start, I will talk about a result that's just been published on the issue of Titan and whether it has oceans. Titan is the large moon of Saturn, and it attracted intense interest in the 70s and 80s when missions showed that it could well have liquid on its surface. Now, when the Cassini mission visited close and the Huygens probe landed on Titan, the only probe ever to land on Titan in 2005, it indeed saw that there were bodies of liquid, and it's ethane and methane because it's so far away and so cold that water cannot exist as a liquid on the surface of Titan. So that's interesting because that means if there were biology on Titan, it would have to have a different biochemical basis from life on Earth. However, the presence of ethane, methane liquid on the surface did not preclude liquid water inside the moon. So liquid water is a pretty abundant ingredient of moons and planets. It just cannot be seen on the surface of Titan. And so radar and indirect measurements from Cassini indicated that there could well be subsurface oceans of water in Titan, which is an exciting result. That data has been reinterpreted, reanalyzed in the presence of some more sophisticated models of Titan, the moon, and it indicated that there was perhaps some other energy mechanism at play at the interface of an ice surface, which reduced the likelihood that there are large subsurface bodies of water. And so the question arose, and the provocative title of the paper was that Titan may not have an ocean at all. It's not a definitive result, and so it's interesting because it takes Titan perhaps off the list of high habitability targets in the outer solar system compared to, say, Europa or Enceladus. But it's not quite as simple as that. The constraints on the oceans, making them less omnipresent and less massive and less large in volume than previously thought, do not preclude the existence of large pockets of subsurface water. In fact, possibly in some cases as large as the volume of the Atlantic Ocean. So, and other people, astrobiologists, have pointed out that if the water inside Titan is more concentrated rather than being a global ocean, that would actually help in terms of the concentration of the chemical ingredients needed to form life. So it does not reduce at all the potential for habitability of Titan, given that there is going to be some liquid water in there. It's just not as abundant and widespread as previously thought.
Excellent. Thank you very much. So for those of you who have questions related to that topic, post those in the chat and we will get to those. In the meantime, we will start with some questions from our live participants. The first one is from Salima, who is interested in becoming an astronaut and would like to know if you have any information about how one can go about the process of becoming an astronaut. And again, this is not a US-based participant. So, what are some of the different ways that somebody from another country can potentially get into space?
Right. Well, the American astronaut program is preliminarily and mostly designed for American-born astronauts. However, the European Space Agency has an astronaut program, and they've been a little more open-minded about it, and they have actually trained astronauts from Africa and Asia, not just from European countries. So I'd say the European Space Agency astronaut application is probably one to do. But these national space agencies have quite limited slots for astronauts. So the number of applicants in each intake cycle is thousands, and then they're reduced painstakingly down to hundreds, and then maybe at the level of a few dozen people get interviews and physical tests, and then they may select 6 or 8 or maybe 10 in a cohort. So it's a pretty tough odds. The private sector, however, is also using astronauts and creating new corps of astronauts. So SpaceX and Blue Origins are also open-minded in how they approach astronaut selection, so they're not at all limited to members, to citizens of the United States. So I'd suggest looking at the websites, especially of Blue Origin and SpaceX, for their astronaut programs. It's still the case, even for the private sector, that the number of applicants and potentially qualified people is going to vastly exceed the number of slots. So it's great to have a dream to be an astronaut, but the reality is the odds are kind of long for anyone, however motivated and however well qualified.
Excellent. Thank you very much. The next question is from another one of our live participants, Elizar, who asks, let's see here. Can you talk a little bit about how Uranus and Neptune, we believe, formed, and how, are they, we know that they, that planets move around. Would they have formed the way they are in our solar system, or have they moved, or should they be ice giants? Like, can you talk a little bit about their formation and movement in our solar system, what we know?
Right. So the solar system has 4 rocky terrestrial planets, Mercury, Venus, Earth, and Mars. Then quite a large gap. Then there's the asteroid belt, and then you have 4 gas giants. And we may distinguish between Jupiter and Saturn, who are true gas giants, and Uranus and Neptune, who you might call ice giants, or they are in a slightly different category because they're smaller. Those outer planets, all 4 of them, including Uranus and Neptune, they formed in the periphery of the solar nebula where the temperatures were very low, and the rocky material accreted into a core. And so these giant planets have rocky cores. The mass is not very well measured, but it's probably 5 to 10 Earth masses. And then around those cores accreted an envelope of hydrogen and helium, which is the primary abundance of the solar nebula. And that grew gradually into these gas giant planets. And that process was quite rapid. It took maybe 10 or 20 million years at the beginning of the solar system, 4.5 billion years ago. In the early history of the solar system, the orbits were somewhat unstable. So there was dynamical processes at play, and it's quite likely in modeling that Uranus and Neptune actually swapped places and migrated inwards somewhat from a larger initial distance out. So yes, giant planets, the gas giants in particular, can move, and they do move. At the present time, however, 4.5 billion years after formation, the planets are in essentially stable orbits, so we don't expect any large-scale rearrangement of the solar system in the future.
Excellent. Thank you very much. The next question is from ABH, who asks, is there any currently known principle, theory, or law of physics that would have been valid in the Planck epoch of the universe during its initial formation?
So the Planck era is the smallest unit of time and the highest amount of energy that can be conceived of within conventional physics. It essentially comes from tracing the Big Bang backwards to an era 10 to the minus 43 seconds after the Big Bang, when all the forces of nature were unified in a super force that we do not physically understand. And there's the rub, that we don't have a physical theory that unifies the four forces of nature, so we don't have a true physical comprehension of the Planck epoch. So the Planck epoch or era essentially marks the boundary of our knowledge of the universe. It defines a distance back in time where there is no observational evidence, really no direct evidence at all. And so we're using inference based on our theory of the Big Bang.
Excellent. The next question is from Cynthiel, I think. It's kind of all strung together as one name in the chat. So the question is, can you talk about the reason for the sun's corona temperature being higher than that of its surface?
Right. It's magnetic processes that are causing the sun's corona to be hot. And when I say hot, the temperature is several million Kelvin, whereas the surface of the sun, the photosphere, the edge of the sun that we see in our eye, is at about 5,700 Kelvin, enormously cooler. So how can moving out from the sun, from the core, temperatures go down from 10 or 15 million in the core to 5,000 at the surface? So why does the temperature then go up? And the answer almost certainly is due to the magnetic energy deposited beyond the edge of the sun by reconnecting field lines and by the dynamic effects of the sun's magnetic field. Those magnetic field lines pushing out into space to a thin plasma and then sometimes reconnecting and depositing magnetic energy represent an enormous input of energy into this diffuse plasma. And so by mechanisms that are not still totally understood, that plasma attains an enormous amount of energy and gets to an equivalent temperature of a couple of million degrees.
The next question is from one of our live participants. Lawrence K. asks, "Hi, Professor. How do you describe or define entanglement? If two particles are entangled, is it correct to say that they are part of a single wave function?"
Well, entanglement is a quantum process whereby the generally distinct quantum properties of individual particles become overlapping. And so in a sense, yes, it's equivalent to the wave functions overlapping. So you have a composite wave function from the two different particles, and the state of one of the two particles is interdependent with the state of the other one. So if you alter one, you alter the other in ways that are predictable according to rules of quantum mechanics. So it is in fact a superposition state, and that's the way we treat it in terms of the wave function.
The next question is from David Gold, who asks, who has been the most prolific painter of astronomy themes over the centuries?
It's an interesting question. Astronomy art is a big field. I'm not completely expert on it, but I know some of the people involved. In fact, I collaborated for decades and wrote textbooks with Bill Hartman, who's a planetary scientist. He's now retired, but he's had an enormously productive career as a scientist and also as a space artist, and he's still working on his space art. He also does desert photography of the Southwest. That's quite impressive. So Hartmann's work I know well. He's in the category of what I would call realistic painters. Some are photorealistic. The modern world of astronomy art includes people who really try and represent things as accurately as a photograph would. Others are more impressionistic. Probably the most iconic and also prolific painter in the history of astronomy art was Chesley Bonestell. He did most of his work in the middle part of the 20th century. His work graced the cover of Time magazine, of Life magazine, Look magazine, back when that existed, these various picture magazines that had a lot of photographs in them. His work is highly valued and pretty valuable too. And he did hundreds of pieces of work in his lifetime, including planetary surfaces, stars, nebula, and so on, all manner of subjects. So Bonestell, I would say, is probably the iconic astronomical painter of the 20th century.
Excellent. Thank you very much. That's not a topic that we get covered a lot, so that was kind of interesting. The next question is from Shlok Palah, who sent an email. The question is, can we genetically engineer microbes to have other genes and modify them to carry out other processes to use to survive in harsh conditions like on Mars and use them for terraforming?
So this is interesting recent research, and the simple answer is yes, it is possible to do this, and it has been done in some cases. So typically it's been done by taking extremophiles, which are microbial species that already have the ability to survive in extreme conditions of temperature, pressure, or acidity, and then tweak their genetic material to make them even more capable of resisting these extremes. So this work has been done, genetic modification has been done. The technique now used, of course, is the CRISPR technique, which is used in a large-scale effort to try and combat disease and so on. But in this application, it's being used to take microbes beyond their traditional comfort zone and make them able to withstand, for example, the surface conditions of Mars. And I know of at least 3 or 4 research studies in the last couple of years that have in different ways tried to engineer microbes to survive on the Martian surface. A condition of high ultraviolet radiation, extreme aridity, extreme cold. Formally, microbes cannot exist on the surface of Mars. The radiation is too extreme and the pressure is too low and the temperature is too low. But microbes have been engineered to exist below the surface of Mars quite comfortably. And it could be argued that, in fact, if that can happen, then they probably should be there now.
The next question is from one of our live participants who would like to know, can you explain what a kilonova is, and generally talk about sort of larger stellar explosions that are larger than what we could think of as a nova or supernova?
Right. So a nova is a recurring stellar explosion from a massive star with an unstable envelope, and it has a repetition cycle, not a strict periodicity though. Supernova is a singular event, that is the death throes of a massive star, either in a binary system, which would be a type 1a supernova, or a single massive star, that's a type 2 supernova. Kilonova is somewhere in between. It's a dramatic, a seismic event of a star, and it is a death phase of a star. It's usually associated with neutron stars in the final stages that leads to a neutron star and an explosion before that. And as the word implies, as opposed to a supernova, their luminosity is maybe a couple orders of magnitude lower than a supernova event. Their frequency of occurrence is also larger because it doesn't take quite as massive a star to make a kilonova as it does to make a supernova.
Excellent. Thank you very much. The next question is from, again, one of our live participants. Sakenzi would like to know, is there any, or what is the hypothetical and or theoretical basis for white holes?
There isn't really a basis for white holes. They exist as a potential outcome of general relativity of our theory of gravity. A portal into another part of the universe caused by curved space-time and a reconnection of space-time between 2 different parts of the universe where energy can flow from one to another, and where it comes out we see a white hole. There's no observational evidence for white holes. It's not even clear how you would look for one. And the theory that makes them possible within general relativity does not really amount to a prediction that they exist. And so I'd say white holes remain in the realm of extreme speculation.
The next question is from Eric Autumn, who asks, what is the relationship between time and mass?
Well, the relationship between time and mass comes about through general relativity, our theory of gravity, where in general relativity, the clock of an atom or a system or a human being, if it came to that, functions it is a function of the local gravity. And so the stronger the local gravity, the slower the clock runs. And so that means mass is implicated. So if you're on a large massive object, and especially a compact object, then the clocks will run slower. And that's a very simple prediction of general relativity. It's been confirmed in the lab, actually, and on the surface of the Earth, where the gravity is not high, but the precision of our experiments is very good. So it's pretty confidently predicted and observed that in situations of high mass and high local gravity, time runs slower.
The next question is from an email from Wendy Traver, who asks, does the fine structure constant imply that, for example, the binding energy of all protons in any nucleus is the same?
Yes, the fine structure constant, one of the very few universal constants in physics, has a numerical value very close to 1 divided by 137 as a pure number. And it relates to the nuclear binding strength, and it relates also to the weak force in the atomic nucleus. And so it speaks to the stability of atoms. And so the fine structure constant were different than the value it has now. Atoms might not be long-term stable, or it's possible they could be extremely stable. We think in the extended theories of physics, there's a prediction that the proton will decay if unified theories are correct, but we've never observed that. So the proton may be extremely stable.
The next question is from Jack, who sent an email. When our sun becomes a red giant star and encompasses our Earth, will any of the remaining planets be in the new Goldilocks zone? So, for example, could Pluto make a great comeback?
Right, that's an interesting thought. Not really, because when the sun turns into a red giant, which is in about 4.5 billion years when the nuclear fuel is exhausted, that expanded envelope will bloat the sun out to the surface, to the orbit of the Earth and close to the orbit of Mars. And there's a large amount of energy associated with that. So the sun will be in a sort of new energy state. And that's why the temperature is so large. Technically, the habitable zone, if you want to think of it that way, will have moved in that phase out to somewhere near Jupiter, not Pluto, but out to about 1 billion miles from the sun. But it's a very transient situation because the red giant phase of a star late in its life doesn't last nearly as long as the main sequence phase, which for the sun is 10 billion years. It's a couple orders of magnitude less for the red giant phase. And so the odds of something developing in a new habitable zone in such a short time, if it didn't already exist, are extremely low.
The next question is from one of our live participants. Remiss Guide asks, hello, Professor. If dark matter really does exist, would we be able to detect it using differences in gravitational waves with the LIGO program?
So LIGO is sensitive to changes in space-time caused by mass distributions changing. And at the moment, LIGO really only has the sensitivity to detect extremely compact objects interacting with each other and merging. So the core science of LIGO is based on black hole mergers and neutron star black hole pairs merging and neutron stars merging with each other. Those are the compact objects. LIGO is not really sensitive to more generic situations of mass loss or changes in mass. So I think we would need an entirely different new type of gravity wave detector to go beyond what we're already doing.
Norv would like to know if you have any other social media accounts. They miss your Twitter account where you posted interesting things. Do you have any other social media accounts that they could follow instead, where they could see some of the things that you post and discuss?
Yeah, I was on Twitter for years. Actually, it was probably going back a decade, and I followed it through to it becoming Elon Musk's X. And I got disenchanted with it, as many of my colleagues and other scientists did. And so I've not been on X, or as it was called now, and Twitter formerly, for about a year. My main social media account actually now is LinkedIn, which is a very professionally useful social media network for people in academia and business and so on. I do have Facebook page too, and we do for our projects have several Facebook pages that got followed. But I would say I'm pretty moderate or low on the scale of social media usage and posting.
Thank you very much. The next question, I'm going to combine a bunch because we have lots of questions on the 3I Atlas comet. So could you talk a little bit about what is going on with this 3I Atlas comet and what we've learned from it and what we might be able to learn from it or things like it in the future?
So the most important thing we learned from 3I Atlas in Interstellar Comet is the fact that we get interlopers, we get visitors from other star systems. In this case, it's a comet on an extremely fast orbit. It's currently having its last moment of visibility as it whizzes through the solar system, and then it will go on and never to recur because, of course, it's moving faster than the escape velocity of our solar system. So it's a temporary visitor. The energy that it's producing is very interesting because it's not just a visible light, and it's been observed by telescopes, but also with X-ray telescopes. So there's some high energy emission coming off of its surface. It's irradiated, of course, by the sun, as all comets are when they get close enough to be in the inner solar system. The idea that was floated for a while, primarily by Avi Loeb at Harvard, that it's an alien artifact has pretty much gone away. There's nothing at all about 3I Atlas. It has unusual properties, but there's nothing at all that is impossible to explain in terms of an interstellar comet. And so that's the working hypothesis of most scientists. But it's important that the amount of data gathered in its very short, brief visit through the solar system is pretty modest. It has been observed by the James Webb, by Hubble, by ground-based telescopes and radio telescopes, so people have been observing it as intensively as they could before it disappears sometime later this week.
The next question is from Almar, who asks, how realistic are asteroid capture projects for science and commerce? Can asteroid materials be used in high-tech manufacturing and nanotechnology?
Asteroid capture, or space mining, if you want to call it that, is a plausible idea for the future. The technology to capture an asteroid is fairly well established. It's rocket science indeed, but it's not impossible rocket science. The Double Asteroid Redirect mission, DART, of NASA was a clever way to show for a binary asteroid that you can alter the orbits of both of them with an impact from a spacecraft. So NASA's demonstrated a technology that would show how you would alter the orbit or trajectory of an asteroid. So judicious selection of an asteroid that's in a near-Earth situation that comes to the inner solar system, it would indeed be possible with the spacecraft and rockets to turn it into a captured object in a long, elongated Earth-Moon orbit. And from that point, yes, you could mine it. So the technology to capture an asteroid has been initially demonstrated by NASA, and the technology to fully do that and capture one is not impossible to carry out. If you do believe some of the geology of asteroids, then the judiciously selected near-Earth asteroid that's 0.5 kilometer across could have $2 trillion worth of precious metals at current day prices and about the same amount or same value of rare earths at present value. And those are extremely valuable and scarce resources on the Earth, and they have great strategic value. So that, of course, is putting dollar signs in the space pioneers' eyes to try and get space mining off the ground. But I would say at the very least it's 20, 25 years away.
The next question is from Dennis Roddy, who asks, when I hear astronomers refer to the known universe, it sometimes seems to imply that the universe has a physical limit. Can you talk about sort of this dichotomy between a limited known universe and an infinite universe?
Sure. The fundamental dichotomy arises from the distinction between what we can see and what might exist. So that's the difference between the observable universe and the entire physical universe, all that there is. And it comes because there's a horizon in cosmology. The horizon comes about because we live in an expanding universe, but it has a finite age, 13.8 billion years. And so there's a limit to the distance that light can have traveled in the history of the universe, 13.8 billion years. And that means there's looking out in space and therefore back in time, there's a limit to the distance we can see. And that's just imposed by light travel time in an expanding universe. It's got nothing to do with whether there's anything further out. And so that's the observable universe, what we can see, where information can have reached us in 13.8 billion years. And beyond that, of course, there could be larger regions of space, more galaxies, more of the same. We don't know how much more. The physical theory of the Big Bang doesn't prescribe how big the entire universe might be. It just gives a model of expansion which tells you how big your observable universe is. So the observable universe might be a tiny fraction of the physical universe. We simply don't know.
The next question is from Christina, who sent an email. Is it possible that rogue planets could, in fact, be dwarf or very low mass stars?
Well, some planets would indeed be massive enough to get to that brown dwarf boundary. So there's a continuum of masses of stellar and substellar objects. When you go to substellar objects, you're below about 7% of the mass of the sun, and that's the boundary for fusion to occur, the lowest form of fusion being deuterium fusion, feeble energy emitting process, less efficient than hydrogen fusion into helium. And as you go below that limit, you are in the realm of brown dwarfs. So these are hot balls of gas. They're massive enough to generate substantial heat by pressure and gravity within them, but there's no fusion going on. They're not stars. And so these are essentially dark objects, and there could be a lot of these. So there indeed could be brown dwarfs scattered through space that we haven't detected and would have trouble detecting. Rogue planets are something different. Rogue planets are planets that are ejected from their star systems early on or late on by gravitational interactions. Perhaps there's a binary system or nearby passage of another star that kicks one or more planets out. And these rogue planets, if they have the escape velocity to take them beyond the star system where they are born, they can travel through the galaxy. And they will be dark objects, of course. They're just planets. They could be planets of any size, actually. Jupiters, Neptunes, Earth-like planets, or even smaller. So there's, by all accounts in simulations, a large number of rogue planets out there. In some estimates, it could even rival the number of planets that are on normal captive orbits.
The next question is from Jane Weidman, who asks, what is your opinion of Dr. Hawking's prediction of mankind lasting another 100 years or so? If you found it was inevitable that humanity would end in 100 years, would you change any current behaviors?
Well, it's a gloomy prognosis, and Hawking was kind of gloomy on this aspect. He recognized that we had a world culture that was unstable due to the tribalism and powers of around the world that are always fighting each other and having wars. He also recognized that we had incredible technology harnessed that we were not really in good control of. And so Hawking put about 100 years on our longevity based on the instability, the possibility of a nuclear war, because there are still many nuclear weapons in existence, over 10,000, and there are new nuclear players, who the bounds on their behavior are maybe looser than they were on the superpowers going back in time. We also have pathogens and biological weapons that could cause mayhem and devastation. And that's apart from the robot or AI apocalypse that people are talking about now. All of that gave Hawking a sense that we'd be lucky to survive 100 years. My personal take is I think if we muddle through the next decade or so, where climate change and global instability are right on the front and center of our agenda, then maybe we'll hit a quieter patch and be able to evolve more smoothly to a longer term future. But it's very hard to put a long term bet on humanity given our behavior up to this point.
Excellent. Thank you very much. The next question is from Synth, who asks, why are inner planets small in size? And could there be or was there a missing planet in our solar system?
Well, inner planets are smaller than large planets or outer planets for a simple reason. The planets all form in a protostellar disk, in a disk of gas and dust, where the collapse takes place preferentially along the spin axis. And so you form a rotating disk, and the star collapses to the center of that disk. There's just less material at smaller radii than there is at larger radii to sweep up into planets. And so just naturally, from the availability of material and the gravity of forming objects and accreting gas onto them, these will be smaller objects in the outer solar system. Then, because they're smaller rocky cores, they have less opportunity to accrete gaseous envelopes, so their atmospheres will also tend to be thinner and much less than an outer planet, where there's a lot more material available, hydrogen and helium, and a lot more time for gravity to add that to the rocky core. So there's a fairly natural explanation for the small size of the inner planets compared to the outer planets.
The next question is from Arif Roni, who would like to know, what do you think about the future of MOOC education? It was unthinkable not that long ago. So do you think it will continue to improve or change? Will the present education system become radically different in the future?
Well, that's an interesting question. So we have a decade of MOOC experience ourselves within our group with Udemy and Coursera. And MOOCs went through after their sort of birth experience in roughly 2012, 2013, they went through a period of meteoric growth. So perhaps the first decade was very strong growth, not exponential, but very doubling every few years, the number of people enrolled. And that sort of flattened off. It flattened off a little during the pandemic. And then after the pandemic, there's continued growth, but it's much smaller. And that's probably just because many of the people who would naturally want to take an online class like a MOOC have already signed up for it and are already taking it. So you're having to reach new audiences. As for the future of MOOCs, well, they have a long-term future, of course, because remote learning and learning on the internet is going to be a thing for the future. And even standard universities are moving more to online learning. So I think online learning is the wave of the future. And hopefully, lifelong learning as a wave of the future. And that means there are more and more adults who are going to go back online. Maybe they went to college a long time ago. Maybe they never went to college. And they're going to just learn maybe for low stakes or not for a grade or without the pressure of exams. And so I think MOOCs will continue to be attractive to those students. Within the MOOC sector, there's a strong push now for credentials that speak directly to job skills. So there's lifelong learning, just of pure intellectual curiosity, such as people who would take an astronomy course. But there's a lot more practical MOOCs out there that are trying to teach job skills and that help people improve their current employment or perhaps move to a new type of employment.
The next question is from an email. Could there have been a hot Jupiter in the early solar system that was eventually swallowed by the sun? Perhaps this could explain the sun's slower rotation rate than predicted by angular momentum.
That's an interesting thought. And yes, indeed, it's possible that there were, in the very early formation of the solar system, there were additional planets that became unstable, spiraled in, or migrated in, and then were swallowed by the sun. Because Jupiter is a very small fraction of the sun's mass, the absorption of one or more Jupiters early in the history of the solar system wouldn't make a big difference to the sun. And it wouldn't actually explain the angular momentum problem that the question also asked about. That's going to have a different type of solution.
As a follow-up to that, can a hot Jupiter eventually turn into a rocky planet after its atmosphere is stripped off by the star?
That is possible in principle. However, in practice, when hot Jupiters migrate in, they get gravitationally tidally locked to their star, so they're always facing the same part of their star. And that distance of that tidal locking is still sufficiently far from the star that their atmospheres, their gaseous envelopes of hydrogen and helium, are being ablated or burned off the planet at a very slow rate. In the modeling, it will take tens or hundreds of millions of years, maybe even longer, for the atmosphere to be fully boiled off by the star. So that's just the fact of their tidal locking limiting the rate at which the atmosphere is torn off.
The next question is by someone you know who asks, Professor, I personally believe that quantum computing will be a major industry or an important, you know, advance in the future. What are your thoughts about quantum computing, its role in the future, and when that might happen?
So quantum computing is coming out of the research lab, but hasn't yet reached the commercial sector. The big companies like IBM and Google, who are heavily investing in quantum computing, they have quantum computers. They have to be cooled, usually to the liquid helium temperature, to function properly. And I think they have coordinated now several hundred qubits. And that's, of course, a tiny fraction of the digital content of a modern computer that's not based on quantum computing. So these are working at a tiny fraction of the capacity of a conventional computer. However, the parallelism implied by quantum computing makes them very efficient for doing certain type of tasks, including simulating the universe. So even 100 qubits in a quantum computer has an enormous computational capacity because of that parallelism of quantum computing. So if this goes up by a couple of orders of magnitude, then I think they're going to be ready for prime time. I think they're going to start contributing to research enterprises. I don't think we're going to have personal quantum computers for 30 or 40 years, however.
The next question is from Thomas Martin, who asks, could you discuss the latest observations we're seeing with the Vera Rubin telescope?
So Vera Rubin is in its shakedown phase, or commissioning phase, as it's called. It's a huge project. It's undertaking large surveys of the sky, and basically they're just shaking down the detector and making sure that it performs at the level that was promised by the people who built the instruments. And so far, it seems that it's doing so. So the kind of data that's being presented or shown to the press and released in press releases is the kind of data just shows the data quality. It's not really survey science yet. When the telescope starts doing its surveys, it will actually have to accumulate data over months to get any of the scientific results that have been promised, because it will observe large chunks of the sky, and it's going to need to troll hundreds or thousands of square degrees and collect huge numbers of objects and bits of information to answer the scientific questions in front of it.
The next question is from Ivan, who asks, how is the age of stars calculated?
The age of stars are calculated essentially by a model. So of all the things we can say about stars, especially individual stars, we can measure their temperature. If we measure their luminosity, we can measure their distance, and we can infer their mass. Other things are much harder to estimate, and essentially we need a model, and age is one of them. So to get the age of a star, you have to know its mass and its evolutionary state. Is it in the main sequence, for example? And then you use a stellar model to predict how long it could have existed to be generating that luminosity at that mass. And we have very sophisticated and mature theories of stellar evolution to do that with. So it's fairly reliable now to calculate the age of a star, but it is an inference based on a model. It's important to know that there's no way to just look at a star and for the data to tell you directly what the age is.
The next question is from one of our live participants. There have been spin-offs technology from a lot of fields of science. and from space exploration, so things like GPS, smartphones. Do you think there are any, or what would some spin-offs potentially be from research in the field of astrobiology?
Well, the biggest spin-off of astrobiology would be the detection of life elsewhere that has a different biological basis from life on Earth, because that would suggest an entirely different way of engineering an organism. We could essentially take that information of a remote organism. We're not going to bring these samples back to Earth unless they happen to be found on Mars, but from another planet in another star system, we'll never get that information back or samples back. However, the knowledge of what the biological basis of that organism is would allow us to sort of reverse engineer that organism on the Earth. And that would be a new form of biology. So that would be a very exciting application of astrobiology.
The next question is from Viomel, who asks, what would happen if a rotating or Kerr black hole were to lose its angular momentum and stop rotating? What would happen to the energy of the black hole?
Well, black holes are losing rotational energy slowly over time. Remember, black holes, according to Stephen Hawking, have a temperature. They have a temperature associated with Hawking radiation, and they are therefore slowly evaporating. They're losing energy. And they're, of course, also losing angular momentum. So a spinning black hole will gradually spin down. If the black hole completely spins down, that's an enormous time scale, far longer than the lifetime of any star in the universe. So it's a very far future event where a black hole spins down. It will still, of course, have its mass, have its gravitational impulse and its force, and have its distortion of space-time predicted by general relativity. So the stationary black hole is not that different an object from a spinning black hole, and we have general relativity formalisms to understand both of those objects fairly well.
The next question is from Sakenzi, who asks, what distinguishes different states of matter? So can these kind of exist together? Do you have to have, when something changes from one state of matter to the next, is it like a huge change? Is it a minor change? Can you talk about what is a state of matter and what's the difference between them?
So traditionally in physics, there are four states of matter. There are solids, which are materials where the atoms have relatively low energy and temperature, and they're held together in close proximity by electrical forces. And they could be in a crystalline form or an amorphous form. So they don't have to be regular the way a crystal is. They can be jumbled up atoms, but that's fairly stable. A liquid is the next highest state of matter in temperature, and that's a situation where it is a physical medium that takes the shape of its container. That's a typical definition of a liquid, but it has higher energy, and so the atoms and molecules are moving around freely within the material. In a gas, the binding energy, that the weak electrical energy that keeps atoms and molecules together in a liquid or a solid, is overcome by the individual energy of the atoms and molecules, and so they fly freely into space and form a gas, and they suffer collisions within that gas, so they have high energy still. And then the highest energy state of matter is a plasma, and that's like a gas, except it's at a temperature where the electrons cannot stick to the atoms, and so electrons are separated from the nuclei, and so we have atomic nuclei and electrons moving around very rapidly, relativistic speeds because of the high temperature, unattached to each other. And that's a plasma.
Excellent. Thank you very much. The next question is from Irfan, who asks, does practical, I'm assuming they mean observational, but does practical astronomy, is it still relevant in this digital era?
Observational astronomy or amateur astronomy, yes, is still relevant in a digital era. Most data is now digital. Most telescopes have CCDs behind them if they're optical telescopes. Radio telescopes take data that's digitized too. So across the electromagnetic spectrum, typical astronomy data is entirely digitized. Of course, that does leave open the possibility of naked eye observing, and amateur astronomy has a valuable role to play. So I don't think that will actually ever go away, even though amateur astronomers, of course, are keen if they have a big enough telescope and enough savvy to connect a CCD to it and take their own digital images.
The next question is from Hernan, who sent an email. And this is related to kind of the discussion that we had earlier about the Earth's habitable zone changing. But can you talk a little bit about how the habitable zones around other stars might exist or change? For example, K and M stars, where we think that the majority of exoplanets would be in the galaxy. How do those the habitable zones in these other kinds of stars change over time?
Right. So it's a good question, and because it makes the important point that the habitable zone around a star is not a stable thing. It's not long-term stable. It evolves. In the case of a star like the sun, the habitable zone evolves as the sun reconfigures itself internally as it ages and uses up its hydrogen. And in practical terms, if you run the stellar model, the sun gradually gets hotter and hotter as it ages before it exhausts its hydrogen. And this is a slow but steady thing, and it's been happening in the past too. And so the habitable zone, where the Earth comfortably sits in the middle of it, eventually will migrate outward. And the Earth will, of course, move out of the habitable zone and be in the place that's too hot for life. And that'll take about 500 million years, so well before the sun dies. How does this work for other types of stars? Well, it's interesting. For more massive stars or hotter stars, they're generally not considered habitable at all because their stellar lifetimes are so short, tens of millions of years, that it's not considered likely that life would have a chance to evolve or have enough time to evolve on a planet around a star like that. Also, as they age, their habitable zone moves quite quickly. And so even if a planet was within the habitable zone of an O or a B or an A star, it would move out of that habitable zone again quite quickly. At the lower mass end, it's the other way around. The star is long-term stable. It has a very long main sequence lifetime. M dwarfs, the main sequence lifetime could be as much as 70, 80, 100 billion years. And so the habitable zone is much closer to the star because the luminosity is lower. The planet may be tidally locked. But as it stays in the habitable zone, that habitable zone is only going to move very slowly over time and over a very long period of time. So while, yes, the habitable zone of the low-mass stars does move as the stars age, it's a very slow, subtle effect, and it's happening over tens of billions of years, far more than the total lifetime of the sun.
The next question is from um, one of our live participants. Um, Ron asks, greetings from Paris. Since JWST is an infrared telescope, how do we manage to get these beautiful pictures in visible colors and frequencies?
Right. When we have an infrared telescope, the James Webb sensitivity does extend to the very red end of the visible range, just below a micron. But generally, it's true that James Webb is a near infrared telescope and mid infrared. These are not visible wavelengths to the naked eye. So essentially, all the James Webb images that you see are not that direct information that it took. They're that information registered at long wavelengths beyond which the eye can see that have been converted into a visual color table. Essentially, you just have a mapping between the long wavelengths that the eye can't see and the shorter wavelengths from blue to red that the eye can see. So it's a sort of distortion, if you like, of the scientific data to make this kind of an image. We astronomers call it false color because they're not true colors at all. And people tend to forget that all the James Webb images they see have had that done to them, and so they're not native images. They're not the data the way the telescope recorded it. But that's routinely done now for infrared telescopes. It's done in radio astronomy and has been for decades, and it's done in X-ray astronomy, where also the wavelengths are too high in that case for the eye to see them.
The next question is from AF, who asks, how do or why do rogue planets get catapulted out of their systems? I've read about gravitational slingshots, but wouldn't that just make them crash into each other since their gravities pull on each other?
So the rogue planet hypothesis depends on the fact that the orbits in newly formed solar systems can be extremely chaotic. And that's typically because the orbits are not circularized. So the objects that form have high eccentricities, so they are crossing each other all the time. And in that crossing, then the gravitational slingshot can easily input enough extra energy to a planet to give it more than the escape velocity. So that's typically how it happens. It could also happen through a collision, but that's maybe a less efficient strategy. So this slingshot or this ejection mechanism operates routinely in the early phase, and then when the planets circularize in their orbits, they're far less likely to interact, and so rogue planets are not created after the first 1% or so of a planetary system's life.
All right, it is 10:59. We're gonna take one final question, and then we have to wrap up for today. Illyria Moon asks, well, actually, before we get to the question, I'll just say thank you all for joining us today. But if you are still with us, can you please go click on the thumbs up button, like this video, and subscribe to our channel? It really helps us out, helps us get the word out. It shows the algorithm that people are watching our channel and our streams, and it pushes them out to more people. Also, it lets you know about our upcoming live sessions. So we will talk about our next live session at the very end, but we'll get back to the final question, which is from Illyria Moon, who asks, hi, Professor Impey, what can quasars tell us about our universe?
So quasars are supermassive black holes at the center of otherwise normal galaxies that are so luminous because they're accretion of, they are black holes. The black holes are black, but the accretion process can accelerate material and emit enormous amounts of energy to allow them to be seen across the universe. They're important because although only a tiny fraction of all galaxies develops the quasar activity, which is to say has a massive enough black hole and active fueling to make it very luminous, they are visible probes across the universe. So quasars are used to understand the demographics, so the mass distribution of black holes inside galaxies. They're used as cosmic flashlights to illuminate dark and dim material along the line of sight, and that's in part how most of the normal atoms of the universe were discovered, because they lurk in intergalactic space, and they were found by using quasars as flashlights. And they are important because they also tell us about the most extreme astrophysics of the accretion zone around a massive black hole. So all of those things are very active fields in research on quasars, and I studied quasars for decades, actually. I did my PhD on a variation of quasars called BLAC objects. So they're pretty familiar to me and close to my heart. So that's a good question to end on. We covered a lot of ground as usual. Comets to cosmology, and I think we have one more on the books for into the new year before the semester starts. The American Astronomical Society meeting is the second week in January, and Matthew and I are both going to that.
Excellent. Yes, that is something I'm looking forward to. And so there's always a lot of really great press releases that come out about new research. So that first week, or that week in January, I guess it's the second week in January, starting on I think it's Sunday the 4th. Everybody watch your news feeds, because there's usually some fun and exciting astronomical research that comes out. And then it'll give us something to talk about when we come back for our next live session, which will be on Monday, January 12th. So we have a 4-week pause, a 4-week break in there. And we will see you all in the new year. And if you want to find out about new upcoming sessions, again, subscribe to our YouTube channel. Hit that thumbs up button. And then if you scroll all the way back to the top of our chat, there is a link there for a Google Calendar, and you can follow the Google Calendar. And I always put the latest live session information on there as well. So thank you all for joining us today. We will see you all in 4 weeks. We hope you have a great holiday season. And if you have a chance to take a nice break and spend time with family, we hope that you have a chance to do that. Take care, everyone. Bye-bye.